So here we have a disk, and it mentions equal and opposite forces acting on the disk. You would think that the forces would cancel, but we're talking about rigid body mechanics, and you can see that the forces are actually off-axis from the center of mass. And so those forces are actually going to present a torque on the disk. And torque is force times radius, or the distance from the center of the mass, sine theta, where theta is the angle between the force and the radius. Those forces are tangential to the disk, and so they're at 90 degrees to the radius, so sine theta goes away. And by goes away, I mean equals 1. And even though they're seemingly opposite in terms of the way the disk is going to rotate because of the two forces, the disk, I have the force on the right pulling down and then the force on the left pulling up, there's going to be a rotation, a clockwise rotation, which we actually consider to be negative displacement from a rotation perspective, because positive displacement is the way angles go, which is counterclockwise. Why do clocks go one way and angles go the other? I don't know, but it bothers me. I googled it. The earliest clocks were sundials, and in the shadows on sundials in the northern hemisphere go clockwise. And so the very early clocks are sundials that eventually became clocks. Clocks kept going clockwise because that's the way the shadows of sundials moved. There you go. So anyway, each of these forces is going to put its own torque on the disk, and so there are actually two torques happening here. So the question asks for the angular acceleration. And so we have Newton's second law that torque is the moment of inertia times the angular acceleration, which is the rotational analog for F equals ma, where m is the moment of inertia. Now, moment of inertia is given in the problem as 1/2 mr squared. Usually moments of inertia are given in the problem, so that's nice. And so angular acceleration would wind up being torque over I. I is 1/2 mr squared. There are two torques, so that put 2t in there. We figured out that torque is Fr, because sine of 90 is 1, and so you have 2Fr over 1/2 mr squared. When you resolve it out, you get that angular acceleration is 4F over mr, choice D. Alright, so here we have a rotating cylinder rotating around its circular axis, or whatever you want to call it, and it gives the moment of inertia in the problem 1/2 mr squared, and it's comparing this, and it says its kinetic energy is K, and it's comparing it to a second cylinder that has double the mass and double the radius and double the angular velocity, and so it wants to know what is the rotational kinetic energy of that guy relative to the first one. Well, kinetic energy is either 1/2 moment of inertia omega squared, or it's angular momentum squared over 2 times the moment of inertia, but it's not asking about the momentum, it's not varying that, it's changing the mass and the radius. So we're going to use the first expression to figure this out. And so the kinetic energy is 1/2 I omega squared. 1/2 is just a constant, and then I've been using alpha for proportional expression, but alpha is now angular acceleration, so I'll just say prop. K is prop 2, I omega squared. And so we're going to need to slip in the mr, 1/2 mr squared for I. And since it's just a proportional expression, we can drop the 1/2 because that's just a constant. So my kinetic energy is proportional to the mass times r squared times omega squared. And so it says we double all of those things. And so 2 squared is 4, 4 times 4 is 16, times 2 is 32. So the rotational kinetic energy of the second cylinder should be 32 times. And so 32K is our answer, and the mark scheme agrees. So impulse is the change in momentum, and we have a formula for angular impulse. But even though they're analogous, the units are not the same, because we can even take a look at the first expression for impulse is torque delta t. Time, of course, is in seconds, but torque is not in newtons. And torque is actually in units of newton meters. And so we have, if impulse is torque times time, then impulse is newton meter second, and then newton, of course, is a kilogram meter per second squared. So if we combine the units up, we get kilogram meter squared per second, which is choice B. Okay, number 4. So we know the moment of inertia of this disk has an initial angular velocity of 15 radians per second, and then a final angular velocity of negative 25. I made it negative because the positive direction is counterclockwise. So in the end, the clockwise angular velocity, that's a shift in direction. That's the negative direction. So there you go. And it wants to know what is the angular impulse. So impulse equation is either torque change in time, that's kind of like J equals F net T, or sum of the forces times the time, or delta moment of inertia times omega, which the analog, let me write down the analog. The analog would be J equals M delta V or delta MV. The mass is not changing, just as the moment of inertia of this disk is not changing, but the angular velocity is. And so the change in momentum, the impulse here. And so, yeah, we stick in the impulse, we stick in the final and initial angular velocities, and so we get 0.5 times negative 25 minus 15, which is 0.5 times negative 40, and that would be negative 20 Newton meter second, and the magnitude of which is just 20 Newton meter second, and has choice C. So number 5 is a basic kinematics problem. When you think about it, it's just rotational. So they give us the initial angular velocity is 0, starts from rest. Final angular velocity is 16 radians per second, and then it does that in 4 seconds, and it wants to know what is the angular displacement. So you can pretty much use like the average speed or average angular displacement angular speed equation, where angular displacement is the average of your starting and final angular velocities times the time. And so we slap that all together, we get 32. Just be careful when you're solving for theta. That's 32 radians, not degrees. Those are two different units. So 5 is B. Okay, so we have a weightless rod of length D, and two masses are on either end, and there is forces on the two masses. They are going counterclockwise, and the forces are in the same direction from a rotational perspective, so they don't counter each other. And so the masses will rotate. And it says, what's the torque acting on the system from those two forces, and what is the angular acceleration? So torque is Fr sine theta, and the forces are at right angles to the radius, and so sine of 90 is 1, and so torque right now will just be Fr. R is d over 2, is half that diameter, and so the torque would be Fd over 2. There are two forces that are acting, so each torque is Fd over 2, and so the two of them together is simply Fd. And so for torque in the first column, it would be Fd, either A or B. But then the angular acceleration of the whole system. Well, the torque for the whole system is Fd, and torque is moment of inertia times the angular acceleration. Moment of inertia is the sum is sigma mr squared. And so we have two masses, and they both have a distance from the center of r. So I have 2 mr squared. So the moment of inertia would be mr squared plus mr squared for each mass. Maybe capital M, because we use capital M for this problem. So therefore, angular acceleration is torque over moment of inertia. The torque we know is Fd, so I slip that in. The moment of inertia is mr squared plus mr squared, where r, the radius, is d over 2. And so if we collect all of our terms together, in the end we find that the acceleration winds up being 2f over md, and so our answer is A. Okay, 3 more multiple choice. There were 9 multiple choice that QBank gave me on this topic. So we have a turntable of mass m and radius r spinning freely about the vertical axis at an angular velocity omega. Moment of inertia is given as 1/2 mr squared. Small body of mass m is dropped close to the edge of the turntable with a negligible initial velocity, so it's placed on the edge. The body comes to rest relative to the turntable. So then it says, what is the final angular velocity of the turntable? So basically, you got something that's spinning, and then you drop, like a turntable that is spinning, and then you drop a mass onto that turntable, and it says the mass comes to rest relative to the turntable. In other words, it's dropped onto the turntable, and then is rotating with the turntable. So in essence, what you did was you increased the mass of the turntable. And so this is very interesting, but this would be considered a collision problem. This is a conservation of momentum problem. And so momentum is conserved. And so we know that the angular momentum of the system is moments of inertia times omega. And then momentum is going to be conserved. It's going to be the same momentum. So I'm not doing momentum initial and final. But the moment of inertia has changed because you added a mass in. And as a result, since momentum is being conserved, the angular velocity will also change. And so the moment of inertia is 1/2 mr squared. And then we just added on the moment of inertia final. I'm adding on that little mass, little m, out at the edge of the turntable, so its position is r, the radius of the turntable. So we need to include its moment of inertia of mr squared. And so the question is asking for what is the final angular velocity. That's going to be the initial angular velocity times the ratio of the moments of inertia. So combining all our terms together, we get that the final angular velocity is the initial angular velocity times 1/2 the big mass over 1/2 the big mass plus m. We can clean this up a little bit if we multiply the whole thing times 2/2. It gets a little bit cleaner. We get rid of the 1/2s, and we wind up with the final angular velocity is the initial angular velocity times the mass of the spinning disk divided by the mass of the spinning disk plus 2 times the mass of the object that was dropped on it, and that is A. Okay, 2 more. We have moment of inertia, 12 kilograms times meter squared, rotating about its axis of rotation with an angular speed of 15 radians per second. A torque is applied to the object so that its angular speed increases to 50 radians per second. What is the impulse acted on the object? So yeah, some multiple choice questions are a little bit tough, like number 7 over here, and some multiple choice questions are just pretty basic impulse questions, like number 8. You just kind of plug it into the equation and you go from there, right? So not a big deal. The answer is A. And then finally, number 9, the last multiple choice, before we move on to paper 2. And we're talking about torque and time and the angular impulse, but the impulse is torque times time, just like regular impulse is force times time. And remember from force times time graphs that the impulse is the integral. It's the area under the curve. So that curve, quote unquote curve for PQR, that would be the impulse, the angular impulse if we're talking torque. And so 9 is D. All right, so those are some paper 1s that deal with rigid body mechanics. But now we can move into the paper 2s, some of which have to do with rigid body mechanics, but in typical fashion with the paper 2s, they combine a bunch of stuff. For instance, number 10 here has multiple parts, most of which dealing with nuclear, but there is a piece right at the end involving a spinning turbine. But I want to break the paper 1s and the paper 2s into separate videos. I'm going to end this video, and then I'll pick up the analysis of the paper 2s with another video. Thank you.